Let's see if we can work through this process of finding the real zeros, the real roots of a polynomial function for a fourth degree polynomial function. Now, since the degree is 4, we know at most there would be 4 real roots, real zeros. There may be less than 4. At the most, there could be 4. Now, looking at Descartes' rule of signs, there's no change in the signs of the coefficients of f of x, is there? It's positive and remains positive. So since there's no change, that tells us that there will be no positive real roots. No positive real roots. And when I look at f of minus x, I see positive to negative, that's 1 change. Negative to positive, that's 2 changes. Positive to negative, that's 3 changes. Negative to positive, that's 4 changes. So Descartes would tell us we'll either have 4, 2, or 0 negative real roots. It's that number and even number less. 4, and even number less than 4 is 2. 2 from 4 is 2. Even number less than 2, 2 minus 2 is 0. Now, we need to find the candidates for rational real roots, if we have any rational real roots. We're not guaranteed, but if we have them, they have to come from the factors here over the factors here. Well, that's nice. The only coefficient I have there is 1. That's going to make things a little easier. But I have quite a few p values, plus or minus 1, plus or minus 18, plus or minus 2, plus or minus 9, plus or minus 3, plus or minus 6. And aren't these also going to be my p over q values? If my q value is just 1, the q value is just plus or minus 1. And actually, do we even have to be concerned about the positive ones? Because we, according to Descartes, we're not going to have any positive real zeros, so we couldn't have any positive rational zeros. So this set of p values is also my set of p over q values, isn't it? It would just be those numbers over 1, which would be the same numbers we have there. So if I have any rational zeros, they have to come from this set. And they have to be negative, because Descartes tells me I have no positive ones, because there was no change of signs in the coefficients of f of x. Well, let's try one. Let's start with negative 1. Let's see if negative 1 is a root. And we do that again with our synthetic division. So I have the coefficients 1, 6, 11, 12, 18. So let's test negative 1 as being a root. Bring the 1 straight down. Leave that one unchanged. Now start your multiply, carry, add process. Negative 1 times 1 is negative 1. Carry that negative 1 over and add. 6 plus negative 1 is 5. Negative 1 times 5, carried over is negative 5. 11 plus negative 5 is 6. Negative 1 times 6 is negative 6. Add. 12 added to negative 6 is 6. Negative 1 times 6 is negative 6. 18 added to negative 6 is 12. If it's a root, that remainder entry has to be 0. So in this instance, negative 1 is not a root. Well, let's try. I don't want to try negative 18. I want to stick with the small numbers. Let's try negative 2. Let's perform our synthetic division to see if negative 2 is a root. Bring the 1 down unchanged. Negative 2 times 1, carry negative 2, add. 6 plus negative 2 is 4. Negative 2 times 4 is negative 8. Carry over the negative 8 to the next column, add. 11 plus negative 8 is 3. Negative 2 times 3 is negative 6. Carry over the negative 6 to the next column, add. 12 plus negative 6 is 6. Negative 2 times 6 is negative 12. 18 added to negative 12, unfortunately, is not 0, it's 6. Again, Having a non-zero remainder tells us that negative 2 is not a root.